In this video, we focus on a reaction we refer to as saponification of esters. The reason why I have an image of a bar of soap here in the background is that the term saponification refers to soap making. And indeed, the reaction that we are going to look at here is the historical route by which people took fats from animals and used those to react and create soap molecules. Specifically, what they were doing was taking a molecule known as a triglyceride from the fat, which the triglyceride has ester groups present in it, and they were removing that ester group and replacing it with a carboxylate anion, or a carboxy salt, in other words. Let's go ahead and take a closer look at this reaction. In a saponification reaction, we react an ester with water and base. This may look very similar to the last reaction where we did acid-catalyzed hydrolysis of esters, with one key exception, and that is the presence of a base. Whereas in the last reaction, we were working in the presence of an acid. So in saponification reactions, what we're going to see is sodium hydroxide, lithium hydroxide, or other bases. What will happen in the course of this reaction is that the hydroxy anion from the base is going to replace the O-alkyl group from the ester. So in other words, we break this bond right here, just like we did in the acid-catalyzed hydrolysis reaction. And this bond, once it breaks, is replaced with the OH group from sodium hydroxide to create a carboxylic acid. However, keeping in mind that the conditions are basic, meaning the pH is relatively high, that OH group of COH does not stay intact. Instead, the proton is lost to create, as the final organic product, a carboxylate salt, like we see here. So initially, this would represent an OH group, but that proton is quickly lost under basic conditions, and that is what gives O-. Now let's try to tackle a real example of this, where we're taking methyl decanoate and reacting with sodium hydroxide and water. You're welcome to hit pause, give this a try on your own, and then hit play to see if you've done it correctly. Remember that when looking at these reactions, if you saw the starting ester and then you saw the plus sign NaOH and H2O, that would be totally acceptable as well. There's multiple ways to write out these chemical reactions, sometimes having the reactants over the arrow, sometimes having them here in line with the methyl decanoate. So methyl decanoate, remember that the O8 part of the molecule refers to the carbonyl group and the chain that is attached to it. So we need here a 10-carbon chain represented like so. And I'm going to check and see how many carbons I'm at here. Remember, start at the carbonyl, and that's number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'm going to scoot this over just a little bit so that I can add my 10th carbon atom there. So now with my 10 carbons in place of my decanoate group, now I'm going to plug in the methyl group. And to do the methyl group, that's really an O-methyl group. So you put the oxygen of the ester group in, and then our methyl. So we have a long carbon chain here. An appropriate way to abbreviate that would also be to instead draw your carbonyl and then write out CH2 in parentheses and put that there are 8 CH2 groups there, and then at the very end put your CH3 group to denote that on this side from the carbonyl over represents 10 carbons, including the carbonyl plus the 8 carbons of the CH2s plus the CH3 group. So these two structures are equivalent ways, and this is a nice shorthand way if you don't quite trust yourself in writing these zigzag lines out in mass. So methyl decanoate reacted with NaOH and water. Recognizing that this is under basic conditions, we are going to have basic hydrolysis, where we are breaking the molecule and replacing the O-alkyl group of the ester right here with our oxygen anion. We replace it with an oxygen anion in the final product rather than replacing it with an OH because of the fact that the conditions are basic. Whenever we see NaOH present along with a carboxylic acid product, know that the carboxylic acid product is not going to remain having its proton COH. Instead, it's going to lose that proton under those basic conditions to give us instead a carboxylate salt. So I've drawn out the carbonyl group over. Nothing's breaking these carbon-carbon bonds. Carbon-carbon bonds are very, very stable. But what breaks here is the carbon-oxygen bond, and that is what gets replaced with the O from the sodium hydroxide. That's going to have a negative charge, and then the counter ion for that is necessary. That's our sodium. And we know it's a sodium because in this reaction mixture, that's the only cation that we have, and that is just a spectator, meaning it is along for the ride. It doesn't actually change forms or participate in the reaction, but it will be present there at the beginning and end to complex with whatever anion is present. The other product of this reaction is going to correspond to the O alkyl group of the ester. So right here, this part that I'm labeling here is what's going to become the alcohol part of the product mixture. So in this case, we have a 1 carbon chain. So it's going to be a 1 carbon alcohol, CH3OH methanol, as the other product of this reaction. Now, you might be saying, why did we make our lives kind of unnecessarily difficult by working here in the saponification reaction with a molecule that has a very long carbon chain here of 10 carbon atoms? Well, for starters, we're kind of just getting started because in the next unit that we're digging into right after this, we're going to be looking at fats, and fats have notoriously long carbon chains associated with fatty acids and triglycerides and other important lipids. So the reason why we worked with this example problem here in this specific example is because these long carbon chains of fats have important implications in the soap making process or saponification. The reason why is that long fatty chains or long aliphatic chains, long chains of carbons and hydrogens, are very, very nonpolar. And what this creates is if you have a carboxylate salt such as this that has a very long nonpolar portion, coupled with, at the other end of the molecule, a polar group or a polar head group, that creates a molecule that is amphiphillic. A molecule that is amphiphillic is one that has both nonpolar and polar groups. So we call this amphiphillic. Amphiphillic molecules, as I've written out here, are ones that have nonpolar and polar groups that are both present in the same molecule. Now, why is that important in the process of soaps? The way that these come into play as soaps is that due to the fact that they have a nonpolar tail and a polar head, due to that ionic bond, is they assemble into structures referred to as micelles. Micelles are spheres where, keeping in mind that like molecules associate with like other molecules, what happens is in a solution of water, so this is my water solution here, drawn out in blue. What will occur is that the nonpolar tails will assemble toward the center of the sphere. So we're drawing a spherical molecule here, a ball, in other words, of micelle. And the interior of that micelle, that sphere, is going to be very nonpolar. So within this cavity, within this interior of the sphere, that region is very nonpolar because all of the nonpolar tails, as we call them, because they stick off the molecule, have assembled into the center of that sphere. And the exterior of that sphere is our head groups, our COO and A groups, which are facing the water. And the reason why they prefer to face the water is because they are relatively water-like. They are ionic compounds, and ionic compounds, like salts, are generally water-soluble. So we see around the circle here, or around the sphere, I should say, that our carboxylate salt groups are going to assemble facing the water, facing the aqueous solution, while the interior is going to be nonpolar. So there's a nonpolar interior of the mycel, the sphere, because of the fact that those nonpolar tail groups associate with one another closely. And what will happen here, and the reason why these amphiphillic molecules are effective as soaps, is because soaps primarily act in dissolving fatty soil and grease. And when we place a fatty substance into a solution that contains a soap forming these micelles, what happens is the fatty molecules present on your dishes or whatever else you're trying to clean get tangled up within the interior of the micelle. So fats are going to associate primarily with the interior part of the micelle. And the reason why they do that is because fats are very like the interior of the micelle because they are also nonpolar. And then on the outside of that micelle structure is this very water-soluble component, and that water-soluble component then helps carry the entire micelle away, with the fat trapped inside of it, away with the water stream, therefore allowing you to clean your clothes, clean your dishes, or clean whatever else needs to be cleaned that has fatty molecules and other aliphatic nonpolar type substances associated with it that would not be washed away very well by water on its own, because water is not very like those types of dirts.